Have you ever looked at a simple soap bubble and seen infinity? Well, it turns out that tucked away inside the super simple physics of a soap film is this absolutely mind-bending mathematical structure. It's an endless labyrinth that shows up everywhere, from nature to cutting-edge manufacturing. So let's dive into this hidden world and really unpack what the gyroid is all about. Okay, so it all starts right here. A simple soap film, like this one stretched across a wire frame. It's just a beautiful example of nature being incredibly efficient. It will always shrink to find the smallest possible surface area to minimize its energy. And that's what mathematicians call a minimal surface. It sounds simple, but trust me, this is the key to everything that's about to follow. Right, so that little film is elegant, but it's finite, right? It has edges. And this got scientists thinking, what if you could make one that didn't have edges? Could you actually create a minimal surface that repeats infinitely in all directions without ever bumping into itself? I'm talking about a perfect, endless, repeating labyrinth. And just so we're all on the same page here, when we say minimal surface, all we really mean is the most efficient shape possible. Imagine it's just perfectly balanced. At any given point, it isn't curving any more in one direction than another. It's this perfect tension that nature just loves because, well, it uses the least amount of energy to connect things. So this was the big puzzle, the grand challenge, to find a surface that follows that same soap film rule, minimum area, but could also repeat perfectly in 3 dimensions. We're talking up, down, left, right, forward, backward, creating one single continuous surface that splits all of space into 2 separate, intertwined maze-like tunnels. And this is where the human element comes into the story. The guy who finally cracked this was a NASA scientist named Alan Shone back in 1970. And it wasn't some single eureka moment. No, his journey was this amazing story of just playful experiments, unexpected teamwork, and a whole lot of hard work. Basically, piecing together a puzzle that nobody had ever solved before. And this is what he found. I mean, look at this. On the left, you've got that simple, finite, minimal surface we started with. And on the right, that is the gyroid, infinitely repeating, impossibly complex. And yet, and this is the amazing part, it follows the exact same physical rules as that simple soap film. It's what's called a triply periodic minimal surface. So let's properly define this thing. The gyroid is a TPMS. Now, triply periodic sounds fancy, but all it means is that its basic building block can be stacked seamlessly, up, down, left, right, forward, back, to fill up all of space with 0 gaps. And minimal surface just means every single bit of it is following that same energy-saving soap bubble rule. So here's the question. How on earth do you even describe a shape this complex? I mean, you can't just sketch it out on a napkin. You need a blueprint. And in the world of math, the ultimate blueprint is an equation, a kind of secret code that holds all the information you need to build this entire thing from scratch. And here it is. This one, beautifully simple line of code, is an incredibly close approximation of the gyroid. Every single point on that tangled surface is just a coordinate, an x, y, and z that makes this equation true. It's the complete genetic instruction for an infinite labyrinth. Just wild. So how does this actually work? Well, when you feed that equation into a 3D modeling program, it starts testing millions and millions of points in space. And it only plots the ones that make the equation come out to 0. So slowly but surely, out of the void, this unbelievably intricate 3D structure starts to emerge. And it reveals this perfect digital blueprint of the gyroid's basic unit. Every single twist, every tunnel, all of it was just hiding inside that one elegant mathematical statement. It's just incredible. Okay, so having a digital model is one thing, and it's super cool. But there's a special kind of magic in actually holding mathematics in your hands. So let's see how this digital blueprint becomes a physical object that we can actually touch and explore. So the process starts with 3D printing. But you don't print the whole thing at once. You start with the fundamental piece, the building block, which is this single gyroid patch. Every single part of the final structure is just made from copies of this one little piece. Next up is the hands-on part. You get students to take these patches and start putting them together, and the curved edges act as a natural guide. It becomes this awesome mathematical puzzle, It turns a really abstract concept into a fun, collaborative, hands-on project. And this is what you get.
8 of those individual patches click together to form one complete Gyroid unit cell. So the code became a digital model, and now the digital model has become a physical thing, from pure abstract math to something real you can hold.
Okay, so it's a fascinating shape, for sure. And the journey from a soap bubble to a 3D model is pretty compelling. But let's ask the big question. What's the point? Why does this specific mathematical structure actually matter in the real world? Well, because the gyroid is, and I mean this, everywhere. Nature uses it to create the shimmering, iridescent colors you see in butterfly wings. Its unique flowing structure inspires artists and architects. But in advanced manufacturing, it's a total game changer. It has this ridiculously high surface area packed into a tiny volume, and it's incredibly strong for how little material it uses. That makes it perfect for everything from better batteries to stronger, lightweight medical implants. And here you can see it as just pure art. This is a 5-foot-tall gyroid sculpture at Southern Illinois University. It takes that mathematical idea and just blows it up into public art, showing off the beauty that was hiding inside that simple little equation all along. You know, the gyroid started as just a thought experiment about an infinite soap bubble, and it ended up as a blueprint for next-gen technology and a source of artistic inspiration. It just leaves you wondering, right? What other profound secrets are still out there just waiting to be discovered, hidden at that beautiful intersection of math, art, and the natural world?